Hi Joyce, we're starting with notes, that way you can make sure to get all of class, then we're going to start recording it as we go over homework questions. So all you're going to miss today is the homework questions on 9.1 and 9.2. No, yes. But you have the answer solution book, and whatever we don't get to, I'm going to tell the other BCers they have the solution book they can pass around tomorrow when listening to the lectures. Tomorrow, they're going to get directions. You're not. I just told the sub. She knows what to do. So tomorrow, go under class notes, like our class folder. Go under class notes, and then there should be a folder for Chapter 9 videos. And I put up a couple videos from last year. Watch the first one, the shorter one, and then you're going to make it all the way through that one. You should get partway through the other at section 9.4, and then on Tuesday, I'm going to be here, hopefully, Lord willing, to be able to help you guys finish 9.4. Homework due on Wednesday. So that's the main dealio. I think that's it. Yeah, I think that's it. Right now they're reading the intro to the section because I thought it was interesting. Interesting intro. Intro that's interesting. Oh. There we go. Happy Thursday, cool kids. Let's get the show on the road, huh? I know. Me too, for other reasons, but yes. Okay. Did you guys figure out exactly how fast e to the x grows?
Faster than x to the 1.
Do you see that? Like on a Cartesian axis with x being 1 centimeter, which is less than the tip of your index finger. When x equals 6, e to the x is ready to go through the ceiling if it hasn't already. And then it goes on when x is 10, it's higher than most buildings. Anyway, it goes really fast. Which is why, because when you guys see e to the x on the graph, you're like, whatever, it looks like a parabola, no big dealio, but does this give you a different perspective? When x is 10 for a quadratic, you're just going to be at 100 centimeters. That's not so high. That's 1/4 the way to the ceiling. Even a cubic would be 1,000, which is great, but raise it to another power, another power, another power. It's not even going to get close to where this e to the x is going, or at least at the distance. And then we saw at the very end, the distance Proximus Centauri is 4.2 light years. And x is only 43. So,
What's more impressive to me, not the how fast e to the x grows, but how long this blackboard is.
that's random. Okay, so, the large blackboard that you're talking about?
Yeah, I thought it'd be funny.
Ha 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 ha. Alright, let's go find section 9.3 and see what's going on. Spaghetti. I like SpaghettiOs. It's one of my comfort foods. It was part of my childhood. I mean, it wasn't because I barely ever had them, but every now and then.
Are you going to make them for practice?
I don't know if people would eat them. Plus, they're kind of hard to make. I would need like a little stove burner like Mrs. Leon. But I do like SpaghettiOs. SpaghettiOs and like grilled cheese. It's like my tomato soup and grilled cheese. But SpaghettiOs are better.
I make easy now.
That works.
I didn't put hot dogs in.
That works also. Or like chicken apple sausages and potatoes.
Humans make yellow rice and they put cheese and then they put these little sausages in there. So good.
Sometimes they make mac and cheese with like chili.
Oh, I see what you're saying.
Mac and cheese, and if you put tortilla soup in it, it's actually really good.
I would never try that one. It makes sense if you're a
You
stone fryer that
pour
you
it on
would try
top.
it.
Yeah. You pour it on top of the mac and cheese.
Huh.
It's really good. Or try it with mac and cheese.
Oh, yeah.
You ever tried
Oh, yeah.
crab and mac and cheese?
Mm-hmm.
Crab.
So basically mac and cheese and most
And
anything.
then
You even
mac
like
and
throw
cheese
broccoli and
and
chicken in
apple
and be like,
bacon.
it's healthy, pretend. Anyway, you guys write in section 9.3, you don't need to write the blue box, but I was just putting it up there so that you have an idea because 9.3 is not on the AP. Doesn't mean it doesn't help us still think through some things that are on the AP, like limits to infinity, etc. It's an application of L'Hopital's, which is interesting. Because usually we don't really think of L'Hopital's as having an application besides just solving limits, which is pretty much all it does, right? But here's an application that's very prevalent? No. Applicable? Yeah. You're welcome. To our day and age. You're welcome.
You copy the
Yes, green box is good. Blue box is just the y. So why this section? Why are we still covering it even though? Well, number one, there's only 4 sections in chapter 9, so our test would be a little bit lame without a third section. And number two, it's applicable, so we'll get there. We might even get to watch a movie, a little one. Okay, long story short, we're comparing rates of functions. Wait, comparing. Why on earth would L'Hopital's or limits to infinity come in with comparing? Yeah, top and bottom, degree test. We were always comparing because we didn't realize that there were applications to it. Now, if you go down below, how can you compare? Well, here's the dealio. And to be honest, we have used some of these terms incorrectly. I've tried not to, but I think I still have possibly used them incorrectly. If we're dealing with or comparing two different functions, f and g, and trying to figure out who's faster, who's slower, who's the same rate, it's going to go with whose degree is stronger, which that works with polynomials, but we still talk about the degree of functions as like kind of like the magnitude of functions, the bigness of functions. When we're taking limits, the slowness, same rateness. You can think about kind of the degree being bigger, the degree being smaller, or the degrees being tied. But to some extent, this might be a little counterintuitive in that you can say that two functions, when they're being compared, one grows faster than the other, or similarly, one grows slower than the other, if the limit is either infinity or 0. What does the infinity show? Just for you guys to state to me. No. The limit as x goes to infinity of f over g equals infinity. How could we say that f is related to g? F is, careful, be precise. F is growing faster than g. All the time? Eventually. Does that make sense? Meaning g's graph might be higher for a small interval, but eventually f is going to overrun. Does that make sense? However, if you look at the other one, if you look at the limit as x approaches infinity of g of x over f of x equals 0, what can we say about the second one? F grows faster than g, or similarly, g grows slower than f. Does that make sense? So it's just an application of limits and what they can tell us about functions themselves. And I use that to say, like, f has a higher degree than g, but technically that is polynomial language, and we have functions way beyond polynomials. Yeah. For number 2, we have grows at the same rate, and this one is a little bit weird. The book calls it a little bit counterintuitive, and here's the reason why. Because if I was to give you something, for instance, like the limit as n goes to infinity of 3n plus 1 all over 2 minus n. Question, what's the limit? Negative 3. How are they growing? The same. But the limit's negative 3. Yeah, but they have the same magnitude. We can say they have the same n behavior models in some senses. They have the same degree. So we've always talked about, not always, but for quite a while, we've been talking about how the 1 is inconsequential, the 2 is inconsequential, and to be honest, the coefficients in terms of their growth and their rate of growth are inconsequential. That would be an understood negative 1, right? But it is a little counterintuitive to say they're growing at the same rate when the limit is a constant other than 1. I think if the limit equals 1, it's more intuitive. But any constant, we can say the degrees are tied, therefore their growth rates are tied as well. Is that cool? Okay, let's keep going. So I kind of like one of the descriptions they were giving on what it actually means for f to grow faster, which is what I've been using a lot, even in Calculus AB, to say f's degree is higher, has a greater magnitude. The best way to say it is f is growing faster. And what that means is for large x values, g is negligible in comparison to f. Negligible? What's that word mean? Yeah, like inconsequential, doesn't really have an effect. It's going to fade away. Does that make sense? So then we get to this other idea of transitivity, which we're not going to stress about too much. Remember, once again, these things aren't necessarily on the AP. We do have some examples on the next page, so just hang in there as to what homework's going to look like. It's not going to be hard, I promise. That's why I'm like, let's bust through notes. But I like the note. The note is super important. And the transitivity, I don't think you necessarily need to write that whole shebang, but I do like the math below. If you know the limit as x goes to infinity of f over g is a constant and g over h is a constant, then we could say f over h. F over h would be f over g times g over h, which would be L times m, which is also a constant as long as L and m are finite and non-zero. Remember, if the limit is 0, well, yeah, then one's faster than the other. Or similarly, if it's over 0, so the limit is infinite, then once again, one is faster than the other. And similarly, one is slower than the other. Where else have we seen transitive in math before? Yep. And algebra. Technically, when you're first talking about things like a plus b is b plus a. The transitive property of numbers, what is it? Parenthesis a plus b plus c is the same thing as a plus b plus c. It's interesting that addition is strictly defined between two objects, which is interesting. But then we can apply that. Two objects become one new sum plus another. You're always adding two things. I heard that recently. I didn't realize it was literally just between two. Because like if you have, even back to kindergarten, like 1 apple, 3 oranges, and 2 bananas. They're like, oh, whatever, I have this many. Wow. But technically, the addition, you're adding 2 objects, and then you're adding the third object, which means you're doing the sum of 2 and then the sum of 2. You're solving the sum of 3 by summing 2 and then summing 2 again. Right? Neither would I.
9 equals 1.
Yeah, I'm like, whatever, just add the 3 together, but you're like, literally. Anyway, that's what kind of brings some more life into the properties, and that literally, if addition is defined between 2, you have to do 2 and then the third. That goes back to that whole, I learned all I needed to know in kindergarten. You guys ever heard of that? The book? It's like basically the most important life skills you learn in kindergarten. Everything else is icing on the cake.
What are the most important skills in kindergarten?
Basically, like starting to count, starting to read, and then how to treat people. Doesn't mean we come on to the lessons. And I do somewhat disagree, like in practical applications, but it's an interesting read. Okay, so let's go ahead and put this all to practice. Oh, not with the marker across the page. Okay, there we go.
Okay.
All right, so how do we do the following? Hold on, zooming in. There it is.
Magic.
Yeah, but not magic. Okay, so, kind of like it. How do we show that e to the x grows faster? How do we show it? Mathematically, from what you've seen today. Yeah. Take the limit as n goes to infinity of, you can do it either way. You can do e to the x over the polynomial, or you can do the polynomial over e to the x. Now, kiddos, I know you can do L'Hopital's, and I know you can repeat it until the bottom goes to a constant, but are we cool to say, yeah, duh, this limit is? Is that cool? Because the polynomial is going to reduce, the e to the x is not, and we go from there.
When it says show that it grows faster, can we just write this, or do you want
Totally fine. Unless it's a more complicated function where you're guessing, but you probably should show the steps to make sure you're right.
Is infinity factorial indeterminate?
Which one?
Infinity factorial is after that indeterminate. No, right? It's infinity.
It would just be infinity, yeah. Because you wouldn't have any negatives or anything taken away from it. It would just be adding to infinity, which is still infinity. And number 5, show that ln grows slower. Just for sake of keeping it the same, we could do ln of x over x minus ln of x. Now this one might be a little bit more interesting. Because if you look at x minus ln of x, you might be like, oh, of course that's 0. Okay, you're cheating now. How would we solve this? Yeah, you are. We'd have infinity over infinity minus infinity. Uh-oh, we have 2 indeterminates. It's very indeterminate. So question, what are we going to do?
Turn up. We are going to
What am I doing? Oops. You see how I transitioned from X to N? Yeah, I was used to sequence language. There we go. Oh no, how do we simplify a complex fraction? 1, 2, 3, freak out, and then solve it. Now what? Can we just multiply top and bottom by x? So the top is just 1 and the bottom is just going to be x minus 1. So if we go ahead and have 1 over x minus 1, question, limit to infinity, who wins? The bottom wins, therefore 0. Oh yeah, of course ln is smaller because I showed that the limit of ln compared to the other is 0. Does that make sense?
Yeah.
Aha. See, this isn't bad. Number 9. Show that x squared grows at the same rate. Okay, this one's a little lame. Technically, according to the notes, I'm not going to go all crazy. Since I'm just showing you the application of limits, we can say, hey, sweet, look, it's a constant, and the constant is neither 0 nor, ooh, look at my grammar, infinity. No, but the answer is 1. And 1 is neither 0 nor infinity, so therefore the rates are the same. Does that make sense? Oh, got it. Sorry. You're like, what? But technically to do this the proper way, the book's going to show something with the transitivity, I cannot say that. Property probably, in a sense of comparing, but you know what, we're good, because we know how to do limits really well.
So, will we have to use the transitivity?
No. You can use limits. I'm showing you what you can do. Does that make sense? So there is a bigger idea behind it, but we'll be alright. How do we show the two functions grow at the same rate?
Change a base formula.
We could do change a base formula.
That way you can pull the ln of 10 out of the limit.
So on top we could do our ln of x, that's just ln of x. Why am I bringing a 1/2 in front before I even change the base? Yeah, the square root. So square root to the 1/2 power, bring the 1/2 in front. Then I have log base 10 of x. Do you remember how to change the base? Yeah. ln of x over ln of 10. Oh my goodness, don't the ln's just reduce? Come on, mental mathers, what's my limit?
ln of 10. Wait, what?
Good.
Oh, never mind.
Either way. Is that okay?
Yeah, just write it down.
And once again, that is not 0. That is not infinity. It's a non-zero constant. Hence, grows at the same rate. Which makes sense. They're both logarithmic, but we've been making a lot of generalities in how we've done our limits and L'Hopital, etc. Ever since Algebra 2, when you first talked about probably horizontal asymptotes and the degree test, which was a very imprecise way of talking about it, but that's okay. In America, we start with imprecise concepts and build up. Actually, it's kind of everywhere. Because all you need to do is show it's a constant, so if you had done it the other way, then you would have had 1 over ln of 100 or 1 over 2 ln of 10, which is still non-zero, non-infinite. Yeah, you're okay. Okay, last application, which makes it applicable. You're welcome, George. Oh no, where is it? Come back. Come back. He was working so well.
I was like, once I get this wrapped, and then yesterday he was like, where's Richmond? I was like, oh, he's in China. He's like, oh, talk about milk in the system. And I'm like, yeah, you already went to Europe, and in March he's going to Vietnam. And then he was like, I haven't been to Vietnam since the war. I was like, this time he's not joking.
He is serious.
Wait, Mr. Europe was in Vietnam.
All right, algorithm efficiency. What? Algorithms? Isn't that just a way of solving? Like the Rubik's Cube algorithm?
I know.
When else are algorithms used?
Computers.
Computer programming. Matrices as well, that's true. But I was referring to computers, wasn't I? Row reducing and how we had to do the algorithm. Those of you that missed it, had fun with linear algebra.
Did you guys have to do it by hand? Did you make him do it by hand?
Yeah,
Yeah.
she made me do it by hand, and then she did the matrices by hand. Oh, that took forever.
VHC's by hand took forever.
No. The reduced row echelon thing.
Yeah, that took forever by hand.
That wasn't just forever. That was forever the day after.
Oh man.
It was.
And if you messed up, you had to go back like 3 steps. Because that's how long it takes for you to figure it
Here's
out.
the question though: is there really a day after forever?
Yes.
No, that
How about
that,
forever?
That's like
Infinity
infinity
plus
plus one.
that day is part of forever.
No, the forever ends.
But what I was questioning was the after. I agree with infinity plus one. That's a thing.
That's well, forever is
Say
infinity.
plus another day.
Infinity plus one.
There you
It's
go.
just infinity.
But it's still plus one.
That's true.
It just gets there faster.
Okay, algorithm efficiency. The fewer number of steps a computer must take to accomplish a task, the more efficient the algorithm. Why does this make sense? And why could it be important?
I want things done now.
You want things done now, and you want your computer to work as little as possible so that they can accomplish the tasks more quickly and be able to multitask better. Multitask? What? How many things do we use computers for? At the same time. You can have your Netflix open, you can have your homework sheets open, you can, well, I use it for 1,012 things. I'm like, just kidding. I'm recording as I have files open, as I have other files open, as I'm loading notes from the previous class, as I'm saving a video from the previous class, as I'm trying to have RunWeb open in order to take, anyway, my computer's thinking about a lot at the same time, which is why he doesn't always do a good job, because, anyway. But we're not talking about whether or not a computer is fast, we're talking whether or not the way something is done is efficient. Are there certain apps that do the exact same thing and yet some do it better than others?
Yeah.
Oh yeah. Which is why before you get an app, you always look at to see the ratings and see how good the app is, how often it crashes, and why would an app crash? Number one, maybe because it's programmed poorly, but number two, maybe because in the sense of it actually has a breakdown in its process. But maybe the other part is just it's not programmed as efficiently as another one. So anyway, real quick illustration. What?
Or you don't have your service. You're not connected to the server.
Or your
Oh,
iPhone's
okay.
not updated.
Oh, so it could be a problem on your side. I'm just saying if the problem is on their side. Like if it's rated low, it's probably not your problem, it's theirs. Wait, I'm going here, but not to here specifically. Nope, yes. Here we go. Webster's third new international dictionary lists about 26,000 words that begin with the letter A. Here we go. Count them. There it is. One way to look up a word in the sense of if you're saying maybe on Google, define colon, or you're asking Siri, what is the definition of? How does she find the right word to tell you? One way could be a sequential search. Literally going through the 26,000 different words or however many words are in the dictionary that they're using until you find a match with each of the letters that you have asked for. But the question is, worst case scenario, how many different words did it have to go through to get to that right one if it's the last word on the list?
25,999.
True. Had to go through that many and it had to hit the 26,000. So it could have taken 26,000 steps, worst case scenario, to get to a word at the end of the list. However, look at the second paragraph. There's another way to, so 26,000 steps. There's another way to find a word, and that's the binary search. This is much more computer programming in the sense of, hey, go halfway through the list and see if it's the right word. If it's not, test the letters in the sense of the sequential order of, okay, A is the first letter, what's the second letter? What's the middle word? Is it before that or after that? If it's before that, sweet, you just cut the list in half. So you only have 13,000 possibilities. Then you would cut it in half again. If you still can't find it, cut it in half again. You still can't find it. What's the maximum number of steps you'll have to take in order to find any one word?
9.
Close. 15. 15 steps versus possibly 26,000 steps. Now, could 26,000 be really, really small if it's like one of the first words on the list and be slightly faster? Yes. But how long? Only for the first 15 words. Interesting. So anyway, binary search is better than sequential search, and why is that true? Long story short, because it has fewer steps required. If we go back to our notes, if I can get there. For a binary search for a list of n items, the binary search is at most, here's what we were talking about, 15 steps for our list of 26,000 words. However, what is it in general? In general, it's going to be log base 2 of n. Let me double check I actually got that right. I think it's log base 2 of n. Oops, wrong one. There you go. Yeah, log base 2 of n. If you want to see the math, it actually goes through the math as to why it is what it is and how it's compared. Oh, sorry, it's up here actually. And it goes through powers of 2, and then it goes through powers of log, and then it goes through the order, or the bigness, the greatness, the degree is how we would use it in the old days, of the binary search. Which, if you guys look at it, logarithmic growth, how fast is that? It's one of the slowest. It's one of the slowest types of growth. So logarithmic growth versus something that's a little bit more polynomial, linear, etc., with a sequential growth, the logarithmic is going to lose, hence it's going to, the number is going to be smaller because the function increases slower, hence the more efficient the algorithms. Remember, we want the smaller for the algorithms, not the greater. So what if we were to look at an example? This one's kind of lame. It has nothing to do with computers. Aw, that's no fun. Misplaced example. You should have been on the page before. Lame sauce. Show that the three functions grow at the same rate. Blah, blah, blah. What would you do? Take the limit between the first two, limit between the last two, and then you could say the first two are also, or sorry, the first and the last are already also related, blah, 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 with a transitivity property, and then you can be done. Okay, sorry, I apologize. Misplaced example. So instead, let's go find the example we were supposed to find, which is number 43. He's here somewhere. Next page. There we go. I have to go steal him. So what's my problem? This guy is supposed to be over there? Yeah. And who do I want here? This guy. Okay, search algorithms. Suppose you have 3 different algorithms for solving the same problem. Each algorithm provides for a number of steps that is of the order of the following functions. Which of the algorithms is likely the most efficient in the long run, which means this is like the worst case scenario, right? Log base 2 of n was the worst case at most how many steps, which we want to minimize in order to have a more efficient algorithm. So which of these is the most efficient algorithm? I'm going to go place it where it's supposed to be. There it is. What do you guys think? Yeah, we want the slowest. We want the lowest. What will we have to do?
Take the limit
Mm-hmm.
of each.
And you do log base 2 of n over everyone.
It's up to you. Because remember, you're just looking to find which ones are 0 or even infinity. You're just going to say, like, hey, based on the 0, it would be the top that I want. Based on infinity, it's the bottom that I want. Does that make sense? Do you guys have the 3 functions written down? Does anybody have it written down? For my purposes, I would probably think, hey, let's change the order of these 2, right? you tell I'm changing the order?
Cancel the ends.
Yeah, I figure if I compare the first two, I can just simplify real fast, right? What's the final limit of the first two? Do you guys get it yet? 1 over log base 2 of n, that'd be 1 over infinity, which would be 0. Who's slower of those two? The first one. And I want the slower one. Because the slower one is the fewer number of steps, which means the more efficient algorithm. Does that make sense? Just because it's growing slower doesn't mean it's slower in process. That means it has fewer steps to it. So now I can go ahead and take the limit as n goes to infinity of n log base 2 of n all over n to the 3 halves. No. Because remember, if it's infinity, I know the bottom's slower. If it's 0, I know the top is slower. I just make a conclusion based upon what I get. This is a bit yucky. Some of you guys go to ln.
Would it be easier if you do the 3 halves on the top? Because that way it won't be.
Maybe. I think either way you do it, though, it's about the same. Maybe first plus first and second. N over n. How can I cancel the n?
Just n to the 1.
Oh, that's easy. Good call. Then I should make that n to the 1 half. So ln of n over 2, which would be 1 over n all over ln of 2 over 2 n to the negative 1 half. Which would be limit as n goes to infinity, n to the negative 1 half, 1 over n to the 1 half, n to the 1 half pops up, which will be 2 over ln of 2 times n to the 1 half over n. Right? Equals 0. So who's the most efficient algorithm? That guy right there. Because n to the negative 1 half is 1 over n to the 1 half. Pop it up to the top. N to the 1 half over n is 1 over n to the half.
No, I mean, you should pull up the ln of 2.
Well, it doesn't matter. It's constant, right? Okay. So where does all of this bring us? Basically to homework. Section 9.3. Due tomorrow. It's fallen off my stool. That is positioned weirdly. However, before we go to homework, there is this lady that homework talked about, which I'm not going to show you a lot about. However, Mr. Moffat, I think it was a couple years ago, showed me an article about her and showed me the following video. I'm not going to show the entire thing. However, if you just search Grace Hopper, the queen of software, cracks jokes with Letterman. She has since passed away. I'm almost positive. Look at Letterman. He was really young then. But she was it a rear admiral, I think, in the Navy? And she basically just went in, probably World War II, if I remember right. Oh, goodness. You're in my way. Thanks. There we go. Talking about Microsoft, yada, 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 ill-advised, yada, 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 et cetera, et cetera. Grace Hopper Conference was supposed to be a celebration of women in technology. There it is. Navy Rear Admiral Grace Hopper, the most important, possibly, woman in the long history of technology. And then they go on to say possibly one of the most important people in the history of technology, period, not just women. But we go on in the sense of she's the one that came up with the idea of talking about a computer bug, which is interesting. That came from her. She made it up. She randomly reacted to something, and she was saying, I think it was because literally there were bugs crawling around in the old computers and like short-circuiting things. Anyway, super interesting. But she had a lot to do with programming language code into something a machine can understand, machines talking to each other, etc., etc. It's a really interesting article. But we're just going to watch just a little bit of it, and then you guys can get your homework done.
Our first guest tonight has credits that are far too impressive for any guest on this program. This woman recently retired from the United States Navy as a Rear Admiral and was, until that time, the nation's oldest active military officer. She is also a pioneer in the computer field as well as a brilliant and charming woman. Please welcome Admiral Grace Hopper. Thank you very much for being here. Have you ever seen this program?
I'm afraid it's too late for me. I have to get up at 5 to be at the office at 7.
You get up at 5 and go to work at 7?
Well, it's a long ways from Arlington, Virginia, across the river and down through Washington. We used to have a boat that went from the Pentagon down to the Navy Yard. Mr. Carter took it away.
Oh, President Carter. Did he commandeer it for private parties or what?
No, he decided he was using too much energy.
Oh, I see. It was a conservation matter. So then you're working a full day now for a private firm, right?
Yes, sir. Digital Corporation.
Digital
We've got to
equipment?
get that in there, get out.
Okay. And how long ago did you leave active service?
31 August, 2400.
Now, see, that's...
It says it's 2400 in the orders, too.
2400 is...
Midnight.
Oh, midnight, yeah. Was there a wild celebration at midnight when this took place?
I was asleep.
You were asleep. So you went to bed in the service and you woke up out of the service.
There's something you learn in your first boot camp or training camp. If they put you down somewhere with nothing to do, go to sleep.
I think that may be office policy for us upstairs, too. Now, Grace, you mentioned boot camp. Now, when did you go through Navy boot camp?
1944.
44. And what kind of...
Smith College.
Was it tough, physically demanding?
Mentally demanding. All those youngsters that came in with me, they could still memorize things, and I'd forgotten how.
I see. So you...
You can't memorize you can't derive the organization of the Navy. You have to memorize it.
So you were older than most of the other enlistees.
I just barely got in. I was 37.
37. Now, what interested you about going into the Navy at 37?
Well, World War II to begin with. That's one of the hardest things to tell people in this country. There was a time when everybody in this country all did one thing together.
And you just wanted to get over there and fight Nazis.
Well, the other thing, I had to go Navy because my great-grandfather was a Rear Admiral. And if I hadn't gone in the Navy, he probably would have risen from his grave and haunted me.
Yeah. So it's a tradition in your family. Yeah. But before that, you also...
I was a college professor.
Yeah. And you worked on the original computer in this country, right?
I was very fortunate. The Navy ordered me to the first big computer in the United States, Mark I at Harvard.
It was called Mark I at Harvard? Now, in those days, the thing was...
51 feet long, 8 feet high, and 8 feet deep.
And that was the pocket model.
You can put it on a little tiny corner of a chip now.
Yeah. Now, how did you know so much about computers then?
I didn't.
How
I was
did
the
you?
first one.
Yeah.
In fact, I had to learn a lot of things. One day, Commander Aiken came around to my desk and says, "You're going to write a book." I said, "I can't write a book." He said, "You're in the Navy now." So I wrote a book.
You had to write a book, and that was outlining the entire
Manual of the computer.
Yeah.
Anyway, pretty cool lady. It's a really cool video. Just search Grace Hopper Letterman. She's really funny. She goes on to talk about the bug and how it actually came about. So anyway, she's a cool woman from history. Accomplished a lot for what we have today. And it was literally just kind of one thing after another happenstance. You guys know what homework is? I'll put it up on the page if you guys want to write down your spirals, and we'll go from there.